Good afternoon. I'm Stuart Hall-Cooper, and I'd like to welcome you to our webinar today on Drainage Design 101. I'm joined today by my colleague Mike Reeves. Mike is our manager of our support team. He's a civil engineer with a background in hydraulic modelling. I'll pass you over to Mike, who will get us started.
Hello everybody. The intention of today is really walk you through a typical project. So the sort of thing that we cover on our training courses A and B. So if you're an experienced MicroDrainage user, I hope there won't be too many surprises. Hopefully it will be confirmation of stuff that you're already dealing with on a day-to-day basis. If you're a new user, then I hope it will be of great use to you. As I say, we're going to walk through a typical project, seeing the sort of typical decisions that we have to make along the way. So before I start, I just wanted to give a little advert for the department that I work in here in Newbury. I run the training and support department. So the way it works is that when you buy the software by MicroDrainage, it comes with a 1-year maintenance agreement. And after that 1 year is expired, the vast majority of our customers will renew that support agreement. And for that, you get two things as part of that agreement. Firstly, every time we release a version of the software, you get that version. And we have a new version of MicroDrainage, which is due for release imminently. So there'll be a nominated representative within your company who will be notified when that release is available. And then it'll be available also to download from our website. So that's coming soon. Also, you get unlimited access to my team here in Newbury. And on the website, this is just a screenshot, we have what's called the support portal. So you'll see within there, you have the opportunity to submit a ticket. So you can ask us any question. That might be something like an IT issue about installing or running or licensing the software. But more usually, it's going to be an engineering question. So if there's something unusual that you've come across or you just want a second opinion on something, then we're here to answer those types of questions. So you submit a ticket. We hopefully provide you with a good answer. And then forever afterwards, you can see in the My Ticket section, there's a record of what you've asked and what our answers have been. You can, of course, also contact us on the support team via email. So the email address is uksupport@xpsolutions.com. That will come directly to the team here in Newbury. And also, you're very welcome to give us a call. And again, that's dealt with by our admin staff, and then you get through to the support team. So do make use of the service. We're here to sort of help you through any problems that you have. So, as I said, today we're going to be dealing with a very typical system, the design of a sort of system that you might come across frequently. So what we've got here is I've got a very rough schematic. We can see over here we have a series of pipes. Now these pipes, MicroDrainage can deal with both storm and foul water pipes. To be honest, foul water is relatively simple in comparison. We have a great deal of understanding about the contributions to foul water systems, the number of people and number of properties upstream of each pipe. Stormwater systems are more difficult. Rainfall presents us with a greater unknown, and it's that I'm going to be focusing on today. But just be aware that the principles of pipe design are the same, whether we're dealing with a storm or a foul water system. So these pipes that we can see here on the schematic, they could be a typical housing development or a retail park or an industrial estate or even a sports stadium or an airport or anything like that. Any sort of new pipe work that you're designing over a reasonable scale, a few hectares, can be done through MicroDrainage. So our first task is to design and size those pipes, and that's what I'm going to be talking about first. What we'll then be moving on to do is to talk about the discharge control that you can see there on the right of the diagram. Now, whatever your system you're designing, you will be discharging into some sort of receiving water course. So that might be a typical stream or ditch, which is controlled by the local authority. It may be a major river controlled by the Environment Agency, or it could be an existing sewerage system, which is likely owned by the water company, Thames Water, Anglian Water, Severn Trent, that sort of thing. So one way or another, there is going to be some control, the amount that you can discharge into the receiving water course. And we're likely to have to put some sort of structure, such as a hydro break, weir, orifice, something like that, to control that flow. So when that discharge control is exceeded, we are going to get backing up into our system, and we're likely to have to store that flow. So we could go for a simplistic design, something like a big oversized pipe or a tank or a pond, or we could go for something more inventive like a subsystem. Whatever you choose, we can represent it and design it within MicroDrainage. So I'm going to be talking through a very, very simple system, just the design of a tank. Okay, so that's what we're going to be looking at. First, the design of the pipes, next, the design of the discharge control, and then finally the design of the storage or attenuation. Now, the rules and regulations come in a wide variety. I won't be going into the details of those today, but one of the main ones that we work with is sewers for adoption. Now, I believe in its 7th edition, and this is page 55. I've just done a screen of sewers for adoption, and we can see here that when we come to design the pipes, there are 2 design criteria. So the first one, section C 5.1 that we have here, is essentially a no surcharge criteria. So what it says is, as we can see in text here, for sites which are relatively steep, which have slopes greater than 1% or 1 in 100, we're expected to make sure that the pipes don't surcharge more than once a year, a 1 in 1 year return period criteria. For flatter sites, it's a 1 in 2 year criteria. So essentially, during these relatively severe storms, we can't let the pipes become full. Next, we have section 5.2, which is protection against flooding. Now, this covers more severe storms. So, say during a 1 in 30 year storm, the sort of storm that you might see only maybe 2 or 3 times in your lifetime, these very, very severe storms, we can't flood during those severe storms. So although the pipes are allowed to surcharge, they're not allowed to flood. There are other criteria, such as the Syria SODS manual, Syria 753, which talks about even more severe storms than these, the sort of 1 in 100 year plus a climate change allowance storms. These very, very severe storms are allowed to flood as long as that flooding doesn't cause any damage. And I'll be briefly mentioning that, although it's not the focus of the study today. So what I'm going to do now is switch to MicroDrainage. And what we're going to do is we're going to start to design a typical project. So the first thing that I do is start a new job. And the first thing that I'm presented with is the design criteria. So the first thing that I'm going to put in is the return period that I'm going to design for. So from sewers adoption, I'm going to assume that I have a relatively flat site, and therefore I'm designing for a 1 in 2 year storm. Now, I won't go into the details of return period. That's a whole massive subject on its own. But suffice to say that it's not simply the worst storm that will occur during a 2 year period. We have to look at longer periods than that. So we might look at, say, a very long period like 100 years and say the 50 worst storms within that 100 years would constitute a 1 in 2 year return period. So it's a big topic in itself, and I haven't got time to go into the details today. The next choice is a choice of which type of rainfall to be using. So in the UK, there are 3 main theories. There's the FSR rainfall, Flood Studies Report. There is the FEH rainfall, Flood Estimation Handbook. And FEH has recently been extended, so there's now FEH 99 and FEH 2013. If you're working outside of the UK, then it's likely that you're going to be working with IDF curves. That's intensity, duration, frequency curves. And they all essentially work on the same theory. Just going back to PowerPoint now. The theory is that, as we can see here, we have 3 different profiles of storms. One that lasts 30 minutes, one that lasts 60 minutes, and one that lasts 120 minutes or 2 hours. And as we can see here, with a longer storm, we're plotting intensity against time here. With these longer storms, the peak intensity is lower, but the volume, in this case the area under the curve, is greater. So as storms get longer, their volume increases, but their peak intensity decreases. This means that any one of these storms could be our worst case scenario. So although they represent the same return period, any duration could be the worst. And typically storms at the top of the catchment will be very short. They would be the worst case scenario. And as we move down the catchment, it's the longer storms which tend to dominate. And those of you who are familiar with concepts such as time of concentration, the rational method or modified rational method, will be familiar with that concept, the way that we have to test for all storms, even though they all represent the same return period, We have to test them all and find out which is the worst duration. And we focus on that a lot within MicroDrainage. So moving back to MicroDrainage itself, I mentioned that there are two rainfall theories, FSR and FEH. And the big question is, which one of these should we choose? The FSR rainfall or one of the two types of FEH? Well, as I said, they're all based on the same concept, that as storms get longer, their peak intensity reduces. FSR is the older one. I think it was developed based on data collected 40 or 50 years ago. FEH is much newer. FSR has the advantage that it's free, and therefore we can include the data on which it's based directly within MicroDrainage. FEH, you have to buy from the CEH website. I'm not going to provide definitive advice on which one is best. I'll only say that you have to do an assessment. Sometimes FSR in your particular location will provide the worst rainfall. Sometimes it will be FEH. So some local authorities will say that you have to pick the worst one. Others will say that you simply go with the later, the FEH-based storms. So it's a choice and it's a discussion, and it's something that should be assessed on an individual project-by-project basis. Today I'm using FSR purely because, as I say, it's freely available to us. It's digitized within the software, and therefore what I can do is just click on a map. I'm going to choose Newbury, and therefore all the parameters are available to us immediately. If I was using FEH, I'd have to go to the website and buy that data and then import it into MicroDrainage. But the theory is exactly the same. So I pick my location, and it's provided the simple parameters that FSR needs. Next, we put in the global time of entry. To find this figure, you look in the Wallingford procedure. That gives some recommended values for that. And that simply represents the time that rainfall takes from landing on the catchment surface to find its way to the nearest manhole. So I'm going to use 5 minutes. I'm going to assume that on average, between the rainfall hitting the catchment surface and entering the nearest manhole, there is on average a 5 minutes delay. As I say, Wallingford procedure provides all those details. The next one is an often overlooked parameter. This is maximum rainfall. Now, what this is there to represent is the fact that sometimes the rainfall, when it's very intense, not all of it can get it actually into the sewers. Some of it is held on the catchment surface due to a lack of capacity in the inlets and gullies. So even though there might be capacity available in the sewer, there's going to be flooding on the catchment surface simply because the local drainage has got overloaded. What I would say is be very careful about this parameter, because it does literally just truncate those rainfall hyetographs that I showed earlier. It will just cut them off at a maximum of 50 millimeters. Today I'm going to put in a slightly bigger value. I'm going to say 99, but again, this has to be assessed on an individual catchment basis. Similar with time and concentration, I'm going to say that nowhere is it going to take more than 30 minutes from rainfall hitting the catchment surface to reach any point in the pipes that I'm designing. And for a small system, that's perfectly reasonable. I also have this foul sewage. If I was designing a combined system, I know that's fairly rare these days, but if we were to assume that there was going to be some unauthorized contribution from the foul system into our storm system, then I could include it here. Today I'm going to assume that we're working purely on a storm system. The next one is PIMP, percentage impermeable. Now, what we're going to do in a second is start defining areas which contribute to these manholes. And I have a choice. I can either say the total catchment area, which drains my manhole, or I can say purely the impermeable area. So just the roads, the roofs, people's driveways that they might have concreted over, that sort of thing. Anything that we might describe as sort of hard standing area. Now today I'm going to set the PIMP to 100%, and therefore when I come to define my areas, they are going to be purely impermeable areas that I'm going to be defining. The next one is a volumetric runoff coefficient. Now this is absolutely the most contentious parameter, I would say, within MicroDrainage. There is a great deal of discussion about what this parameter should be. These values that we use and that you see here today, these are default values, but they're not necessarily the ones that we would recommend. They've just been in the software for many years since it sort of started. We won't change them, but we do strongly recommend that you assess what this should be on an individual catchment basis. There is a groundswell of opinion that these values should perhaps be increased. In the design method that we use the modified rational method, and therefore this 0.75 that you see here is then multiplied by a factor of 1.3. So we actually get much more than 75% runoff. Well, what it's saying is at the moment, by default, 75% times the 1.3 is then multiplied by the rainfall landing on just the impermeable area. So we get about 100% runoff from impermeable areas and nothing from permeable areas. So any rainfall landing on grass verges, back gardens, that sort of thing, will not provide any contribution under this assumption. And as I said, there is a lot of debate about whether this value should be increased, particularly in catchments that have a sort of clay soil where you might expect permeable areas to provide a contribution. So again, this is a discussion that should be had when it comes to setting these standards and on an individual catchment basis, depending on where you are in the country. Okay, over on the right hand side here, we have some much less contentious values to put in. We have a standard list of pipes and manholes. So our standard list of pipes starts at 100 millimeters, then goes up to a diameter of 150 millimeters, and then increases in 75 millimeter increments from there. So 225, 300, 375. That's the library, if you like, that it's going to be choosing from when we come to design these pipes. If you want something different from that, you're very welcome to customize this list. So if you have a pipe provider who builds 275 millimeter pipes, you would just include that in this list. Similarly with the manholes, is that there's a standard library. The relationship between manhole size and pipe size is standard. You can edit that if you need to. When we come to design these pipes, we then have a choice between laying them, the soffit, so the top of the pipe should be level, or whether the bottom or inverts of the pipe should be level. Now, I've never worked on site myself, but I'm told it's much easier to lay these pipes when you have pipe size changes so that the tops of the pipes are all at the same level, so you can look along them and make sure that they're all perfectly in line. So by default, we choose level soffits. We then have a parameter which deals with additional flow or climate change. Things like urban creep can be involved in this parameter. I'm not going to be using it today. We then have other design parameters, backdrop, minimum, maximum backdrop height. Again, this comes from sewers for adoption, just good practice in building pipes. You don't want the difference between two pipes in the vertical plane to be too big or too small. Also, we've got this minimum design depth. By default, you want your pipes at least 1.2 meters below the ground, although that can be changed either globally or on an individual pipe basis. We also want some velocity in the pipes, and we want to give these pipes some slope so that we don't have sort of dead spots or siltation building up too badly in the pipes. So that's a very brief whisk through of all these design parameters. As I said, courses A and course B that we run here in Newbury go into these in much greater detail. So I've set up my design parameters. First thing I'm going to do is now design my first pipe. What I could do, if I wanted to, just back to the PowerPoint presentation, I could digitize all these pipes within the DrawNet feature that we have within MicroDrainage, or within another package such as AutoCAD or Civils 3D. And this is a screenshot directly from AutoCAD. So we can see that MicroDrainage is actually embedded as an add-on. The DrawNet facility is actually embedded within AutoCAD. So we digitize the locations of our pipes and the contributions to those pipes into AutoCAD, and then just open it in MicroDrainage and it would all be there for us. And what this slide also demonstrates is that MicroDrainage has a very specific numbering system. The first pipe in our system must be pipe 1. Any branch that comes in must be numbered consecutively, so branch 2. And then as we move downstream, we add the suffix number. So 1001, 1002, 1003, etc. as we go down the system. Again, that takes some learning and some getting used to, but just for now, understand that there is a very specific numbering system that we have to stick with. Back into MicroDrainage then, we choose our first pipe, pipe 1. We're asked to give it a length. This could be from, say, AutoCAD if we digitized it there. We specify the area which drains to that pipe. So remember, this is the impermeable area. Time of entry, that's been set up for us in our global parameters, so as pipe roughness. We then put in the cover level. So if we were using a DTM, it could be read from that, or we can just type it in ourselves. So we put in some basic information. We know how long the pipe is, we know the area draining to it, and we know the ground level. When we click down now, we can see that it's given us the size of that pipe. So based on the modified rational method, it's designed the pipe as a 225 millimeter diameter pipe. Okay. So what I'm going to do now is pick one that I've put in some data for earlier. And we'll see we've got some branches in there. If I look in the sort of spreadsheet or network details view, we can see all that set up there. Once you've designed some of these pipes, it starts giving you some results about the flows within those pipes. For example, if we were to look at pipe 1001, we can see that the capacity of that pipe is 160.4 litres a second, but currently we only have 124.6 litres a second going through it. So that pipe, we could put some more flow through it without having to go to the next pipe size up. So it's slightly over-designed at the moment. We couldn't come down a pipe size, that wouldn't give us enough capacity. So it's found the best optimized design that it can. Now at this stage, just going to have a look at this in the long section view. And we can see at the moment, it doesn't look particularly sensible. We've got the ground levels up here around 100 meters, which do look sensible. But then all the pipes are down here at the bottom. They've got a sort of naught invert level, something like that. Now we have a really clever special button, which is our optimize button. Press that button and it does all the clever things based on the design parameters that we've just set up. Say yes, we want to continue. It's created these invert levels based on things like the slope and the minimum cover that I just showed. And now when we look in the long section, it looks a lot more sensible. So we've got all the pipes moving downstream there. You can see we've got the ground level and we've got the pipe, soffit and invert level shown there in yellow. And even in cases where the ground level raises as we go downstream, the pipes obviously still have a positive gradient and slope downstream. All that's set up for us. So that's stage one, designing the pipes. I'll just show you one more thing while we're here. We've now designed those pipes so that they don't surcharge during a 1 in 2 year storm. What we now want to do is check them for flooding. The way that we do that is using a seasonal return period wizard. So what we're going to do is now run some more severe storms through that pipe network that we've just designed. So again, I'm going to choose Newbury. These values change exactly where you click on them. So Newbury, I know, gives us a 19.7 M560, so I'm just going to type that in. We then, as I was talking about earlier, duration, it's all about duration and making sure that you pick the worst duration. So I'm going to run a whole range of durations. I'm then going to run it just for the 1 in 30 year storms. I'm not going to choose a climate change parameter. This time increment screen. There is a lot to say about this. I just haven't got time to go through the details. What I would say is you really need to know about this. This is model stability. It is perhaps one of the most important things to understand within MicroDrainage. There is a place in the help. We have a section called How Do I? Read How Do I number 20. That talks all about stability, what it is, how to spot it, and how to solve it if you do have an unstable model. For now, I'm just going to click Finish. Goes through, runs these series of simulations. Now, what we've got here is we've shown that some pipes are surcharged. That's okay. During a 1 in 30 year storm, we're allowed to surcharge as long as we don't flood. However, at the moment, we're only looking at one storm. We're looking at the 15-minute, as we can see here on the left, the 15-minute summer storm for the 1 in 30 year event. We want to make sure that we've got the worst case scenario, the worst duration of any storm. And there is another really magic button. This only comes with the APT module. You have to have the APT module to be able to access these seasonal return period wizards and this magic button, but it's this one. It picks the critical storm. So you can see what is the worst case scenario. In this case, I've got a relatively small system, and it is the short storms that dominate, the 15-minute storms. But for a bigger system, we might have some longer storms, and they would all be referenced under the event here. So I've designed my pipes. We can see that they're not flooding during the 1 in 30 year storm. We know that they work for the surcharge criteria and they work for the flooding criteria. What I'm going to do now is move on and design that flow control that controls the discharge into the water system. Now to do that, we have a separate utility called source control. It's perhaps one of our simpler modules. I would say it's one of the most useful as well though. And the idea is that the limitation of discharge into a watercourse, you might simply be told what that is by, say, the water company, or a common criteria is that once the design is complete, once your housing development is built, you mustn't discharge a greater rate into the receiving watercourse than you did before the housing development was completed. And what we describe that as is greenfield runoff. So what we say is our post-development discharge rate mustn't be greater than our pre-development or greenfield discharge rate. One of the things that source control allows us to do is to determine what that pre-development greenfield discharge rate is. So under File, we just go to this rural runoff generator. Now there are a number of different theories about what that should be. And you can see the most common theories used in the UK are presented here in this series of dialogues. I'm going to choose ICP SUDS, what I'm going to work on today. We're going to put in the area draining to our system. That's the one file that I just opened in MicroDrainage. So I'm going to put in 1.88 hectares. That's the impermeable area. I use the map again, choose Newbury again, where I happen to be working. I think Newbury's in region 6. We've got a map here where you can choose Newbury's just on the boundary of these two. And then I calculate. And again, there is a whole subject on this, which we cover in training course G. We go to exactly how these numbers are derived. But for today, just be aware that I'm going to be designing to a discharge rate of 9.6 litres a second. That's our Q-bar rate. And as I say, exactly how we arrive at that number, the theory of it, takes a couple of hours to explain. But that's simply how you do it within the software. We've arrived at 9.6 litres a second. So remember that number. Whatever device we design, whether it's a weir or an orifice, a pipe or a hydro brake, something like that, the function of that is going to be to limit the discharge to 9.6 litres a second. So the next thing I'm going to do is design my storage tank or substructure upstream of that flow control device to store those excess flows during the severe events so that we only release them to the receiving watercourse or existing system at a maximum rate of 9.6 litres a second. Now this is a multi-stage process. And the first thing that we do is we do a quick storage estimate just to get us in the right ballpark. So I'm going to choose the FSR rainfall today. I'm going to choose a return period of 1 in 30 years. That's what I'm going to design my tank for. I'm going to do it in Newbury again, 9.7. I've got these highly contentious CV values. This is the runoff coefficient. I've got an impermeable area of 1.8 and I've got a maximum allowable discharge of 9.6 that I just calculated. If I was designing a SUDS structure, I could have an infiltration coefficient. Not in this case, it's just going to be a traditional structure. So I press analyze, it goes through, it runs all those different combinations of storms. And what we end up with is a quick storage estimate. So an initial guess, we're going to say that this thing that I'm going to build is going to be somewhere between 591 and 876 meters cubed. So my first guess is going to be somewhere in the middle of those numbers. It's going to be, let's say 720 is going to be my first guess. Back to PowerPoint. I'm going to be designing a tank that looks like this. So we've got 1.88 hectares draining to it. It's going to be designed for a 1 in 30 year storm. My discharge is going to be 9.6 litres a second. Now on my site, my ground level is at 97.4 near the outfall. And I'm limited. I'm discharging into a water course or an existing sewer. And because of that, I can't go too deep with this tank. I'm going to say that the lowest I can dig down to is 95.75. Now I'm going to set it so that it's 1.5 meters deep. And I'm going to set 0.15 meter freeboard so that we are not in too much risk of flooding. And although it's not drawn very well here, this tank is at a side slope of 1 in 4. Now that number has been chosen for sort of safety reasons. We're going to assume that if somebody fell into this pond, if the side slope was 1 in 4, they could probably climb back out of it again. So it's not for a hydraulic reason, it's purely for a safety reason that we're designing this tank. And as I've just done my quick storage estimate, I'm going to make the initial guess, and it is just a guess, that the size of this tank is 720 meters cubed. So let's have a look at putting those values into source control. So I'm asked to put in my rainfall data. I've got no additional flows coming in. You can see the whole range of SUD structures that we have to choose from here Today I'm just going to do the simplest, the tank or pond. The outfall is going to be, again, a huge range of what we could choose. I'm going to choose a hydro brake, and I'm also going to have an emergency overflow weir if things get really bad, if we get hit by that 1 in 100 year plus 40% climate change storm. Okay, so it takes me through and I set these up. A lot of this has already been done for me because I've done my quick storage estimates. So we've got the 1 in 30 year storm, the Newbury characteristics, that sort of thing. We next come to describing the catchment upstream of it. Now you remember it was 1.88 hectares. Now we've got to describe whether this catchment is steep or flat, long and thin or short and circular, a sort of whatever shape it is. So we're just trying to describe that simplistically with this time area method. And the best way to get that time area method is from your MicroDrainage MDX file. So these set of pipes that we've just designed, I can save this time area diagram. So I'm going to save it, I'm going to call it Mic1. And then when I'm in source control, I then import that file that I've just created, and that gives me my time area diagram. So we can see that although this catchment is 1.88 hectares, 1.106 of those hectares is going to input in the first 4 minutes. Now I'm going to set up the details of my tank. So, sorry if you have to remember back to that drawing, but the cover level is 97.4. My invert level is 95.75. And the depth of my tank is 1.5 meters. Right, this is perhaps my favorite bit of source control. This is really neat. So even experienced users are sort of surprised and delighted by this feature. We've got this calculate button in here. So what we do is highlight the 2 cells, go into the calculate button, and the first thing we do is set aside slope. So you remember it's 1 in 4, purely for safety reasons. I set that up. What it's done is it's given me a sort of cone. That cone has a side slope of 1 in 4. What I then do is go back into it again, use the calculate button, and this time set the volume to my initial guess of 720 meters cubed. So now we have a cone that has a side slope of 1 in 4 and a volume of 720 meters. Okay, I know this is done via spreadsheets, hand calculations. That little calculate button takes a lot of the work of that out. So that's my initial guess. What I'm now going to do is set up the details of my hydro brake. Bottom of my tank is at 95.75. We can't go more than 1.5 meters deep. Design flow is 9.6 meters. And according to these hydro brakes, we have libraries of hydro brakes provided to us by the manufacturers. It gives us the particular type of hydro brake that we're after. Okay. So that's set up for us. The next thing I'm asked to do is put in the details of that emergency overflow weir. Because it's an emergency weir, I'm going to make it pretty big, 5 meters. And the crest level is going to be just below my ground level. So I'm going to set it as 97.25. That's to provide the 150 millimeters of freeboard that I talked about earlier. So I'm all set up. I hit go. It runs all those storms again so that we make sure we've got the worst case. And what we can see here is the one I'm looking for, highlighted in red here. We now know that the 480-minute storm is the worst case scenario. And during that storm, I had 1.411 meters of depth in that pond. Now, I'm allowed 1.5 meters. So this pond currently is a little bit over-designed. So what I can do is perhaps go back and optimize that design. I go in, I edit my tank. Now, 720 was over, so I'm going to guess, and it is purely a guess, I'm going to set the volume to, let's say, 640. And now run it again. Remember, 1.5 meters is critical. Under that, and we're okay. Over 1.5 meters, and we're not okay. So we can see now that we're on 1.506 meters. So a much better guess, this time slightly over. So third guess, I'm going to say, so 720 was over, 640 was under. Let's go for 660. I'm going to set the volume to 660. Okay, and run that. Okay, now we're at 1.49 meters. So I'm 10 millimeters underneath that emergency overflow weir coming into operation. So I don't think we'll get better than that. It seems that we're pretty well optimized now. 640 meters cubed is the size of our tank that we need to look for. Okay. This is still just an estimate. Remember that time area diagram? We were doing a simplistic representation of the catchment. What I now want to do is take this back into MicroDrainage and check that it actually works with the pipes that I've just designed. So what I do is save that file. Let's give it a name. Let's call it source control 01. Save that. And now back into MicroDrainage, what I'm going to do is add that tank in that I've just designed. Now, this is training course B. We talk a great deal about this. It takes several hours to go through the details of this. So, I'm rushing through this and just giving you an overview and a flavor of how it works. But what we do is under network, we pick our storage type. We choose the pipe on which it sits, and it's going to be the most downstream pipe, the one just before we discharge. Again, we have the full range of choices of substructures, which is another huge topic for another day. Training course F also talks about those. I'm going to choose the tank or pond and then import the source control file that I just saved. And it gives me the characteristics. You can see here exactly the same characteristics as were in source control, 640 meters cubed, 1.5 meters depth. So that's now in MicroDrainage. I'm now going to import that hydro brake that I just designed earlier. That sits on the same pipe. Again, big choice of different types of structures. I'm going to choose the hydro brake. It's going to be, remember the bottom of my tank was at 95.75. The design head was 1.5 meters. And the design flow, remember greenfield runoff or whatever has been specified, but in this example it's going to be 9.6 litres a second. So goes away and does those calculations and pulls that in. Final thing I want to do is include that emergency overflow weir. So we put that in. Again, 104. The control type this time is going to be a weir. If that weir discharged to another point in the system, we could link it back into that. We're not going to do that now, but we can have loops and that sort of thing. And as you remember, exactly the same characteristics as were in source control. So a width of 5 meters and a crest level of 97.25. So I've now got everything that I need in there. I've got my network system, all my pipes that I've designed in MicroDrainage. I've got my flow limitation device, in this case a hydro brake, that I've designed based on greenfield discharge characteristics. I've got my storage device, which stores the controls when they exceed 9.6 litres a second. And I've got an emergency overflow weir. The only thing to do now is to run that through the seasonal return period wizard. So again, you need the APT module to do that. Run it through and see if it works. Okay, same storms, same 30-year return period. Big issue about stability, always check that. How do I number 20 is how I do that. And then run that through. Okay, so remember when we get in here, we have to make sure that we've got the worst case storm. This is the magic button to pick that. And this time we can see that there are some longer storms which are causing problems because that tank is taking so long to discharge. It's actually a 480-minute storm, which can cause us the worst case. And some of the pipes are surcharged during this very severe storm, 1 in 30 years. That's okay. There is a flood risk. It gets very close to the ground cover level at this bottom pipe, but it's fine. The main thing is there's no overflow going over the emergency weir, so we're all fine. In fact, if we look at the water level, the level of this weir was at 97.25 meters. Whereas in our results, we can see the worst case scenario is at 97.204 meters. So we've got 46 millimeters to play with. The maximum water level is 46 millimeters below the top of that weir. So let's just try. Let's see if we can reduce the size of that tank just slightly. So I'm going to go back in here, use my favorite button again. Let's set the volume with 660 we had. Let's see if we can get away with 640. Run the seasonal return period wizard again. Just going to run it all through there. So we've got a slightly smaller tank. Hit the critical button to make sure we've got the worst case scenario. And we can see we're now at 97.231. So we're just 19 millimeters below that emergency weir. I think that's as far as we can push it. So we're going to go with a tank that's 640 meters cubed, side slope of 1 in 4. We can see that the maximum discharge rate into our water course is not exceeded. We're at exactly 9.6 litres a second there. So we're all good. If we want to delve a bit deeper into those results, we can do. So I can use graphs. And this is another recommendation that I have, is that graphs are a really excellent way of assessing what's going on. We've got the graph tool there. So I'm going to look at this, for example, is the flows coming into pipe 1002. If I look further down the system, say 1004, we can see that the blue line is what comes into the tank, whereas the red line is what comes out of it. And we can see that we've got over 400 litres a second coming into the tank, but our discharge from it is limited to 9.6 litres a second, and hence that's why the thing fills up. And we can see that the volume during this particular storm only reaches 240 metres cubed. If I was to switch to my critical storm, we should see it fill almost all the way up to 640 metres cubed. The final recommendation is to use the graphing a lot to just assess and check what's going on. So I think that's about it. I'll move back to PowerPoint now. So we've designed this tank. We've designed its limited discharge. We've designed the pipes upstream of it. All very, very quick. As I say, it's normally 2 days to understand all the issues going on here. So I'll hand you back to Stuart just to provide you with some closing comments.
Thank you, Mike. Just having a look at some of the other things that we have in our portfolio, other products. We've covered today the detailed drainage design aspect of MicroDrainage. We didn't really touch too much on the SUDS design aspect of things, which we have an MD SUDS module for. For those of you who have an interest in flood risk assessments, consequence assessments, we have a couple of tools for XP Swim and then XP Storm. And then our road design tool, XP Site 3D. If you've watched any of our webinars in the past, you'll know that we do dip in and talk about these and provide case studies here and there. And in the coming months, we'll continue to do that. We do have a series of training courses running over the next few months, but one I wanted to highlight with you now is one that we're running in Leeds. Ordinarily, we run our courses in Newbury or on site at customer locations, but we have an open one in Leeds on the 25th and the 26th of April. There's a web address there, xpsolutions.com/training events, where you can register and sign up to attend. Going to be more suitable for our northern customers. We are in the process of running a series of workshops across the country. At the beginning of the week, we ran a successful one in London. Our next one will be on the 21st of March in Birmingham. We have one in Leeds, which actually follows the training courses, which I've just mentioned. In May, Bristol. In June, we're in Newcastle. And in July, we'll be in Manchester. And more immediately, events we have coming up on the 1st, so next week, we have XP Site 3D training here in Newbury. From the 6th to the 10th of March, we have some microdraining courses running also in Newbury. On the 15th of March, our next webinar, this will be part of our modelling stream. We'll be looking at the new XP Swim 2017 release. 21st of March, as I mentioned, is the workshop in Birmingham. And then at the back end of March, on the 29th, we're going to be looking at MicroDrainage 2017. It's very worthwhile watching both of those and signing up for any of those events, particularly if you're in the Birmingham area, joining us there.
People are very welcome to ask questions. You can see the email address on the screen there. We'll try and get to those in the next few days and provide answers individually to those people who ask them.
With that, I'd like to thank you very much and hope you enjoy the rest of your day.
Thanks. Bye.
Take care. Bye-bye.